Magnetic forces and currents going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now in the last lesson we learned that charges in motion can experience a magnetic force in a magnetic field. Well, since currents are composed of charges in motion, so can current-carrying wires as well. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So before we get too far into talking about current-carrying wires, just a quick reminder that when you see a current labeled on a diagram in a physics course, it is referring to conventional current. So, and in this case, the conventional current is flowing to the right. That is the imaginary flow of positive charges to the right. Again, the truth is there's really electrons flowing to the left. But again, just want to remind you about conventional current on the diagrams here. All right, so in the last lesson, we learned that charges in motion can experience a magnetic force in a magnetic field. Well, since current in a wire is the flow of positive charges, you have positive charges in motion, there will also be a magnetic force when placed in a magnetic field if it's in the right orientation. Now, if you recall, we learned that if the velocity of the charges in motion are either parallel or anti-parallel to the magnetic field, there will be no force. The same is going to be true here for the current. If the angle between the current and the magnetic field is either 0, parallel, or 180 degrees anti-parallel, then there's going to be no force in that case as well. And the force is also going to be at a maximum when they're perpendicular to each other, the current and the magnetic field. So it's not surprising that we see a sine theta in this case, and instead of theta being the angle between the velocity of the charges in motion and the magnetic field, it's going to be the current and the magnetic field. But again, keep in mind that that current is essentially the velocity of these imaginary positive charges in motion. So it's kind of very similar. The equation says that the force is equal to the strength of the magnetic field times the magnitude of the current times the length of the wire, and then times that sine theta, again, the angle between the current and the magnetic field. Now, if you look, again, this is really all derived from the last equation we learned in the last section with F equals QVB sine theta. So, and if you look here, well, what do they have in common? Well, they got the sine theta in common, okay. They've got the strength of the magnetic field, B, in common. The only way these are effectively equivalent then is if Q times V is equal to I times L. Well, let's see if that's true. So Q times V equals I times L. Well, remember that current is charge over time. So in this case, delta Q over delta T times L. And so here Q, and then velocity is delta X over delta T. So, and if we make the delta X here, the entire length of the wire that we watch current passing through and stuff like this, then L and delta X would be the same, and we'd end up with very similar looking expressions. And that's why we can really derive this one from the one we learned in the last chapter. Okay, so the calculations with this equation are fairly straightforward. It's a lot of plugging and chugging, just like we saw with the last equation in the last section. But we have another right-hand rule, but that right-hand rule is going to be very similar to the one we saw before. And so in this case, we're once again going to put our fingers in the direction of the magnetic field. And instead of velocity, it's going to be current with our thumb. So, and then that's going to leave force coming out our palm. And so the only difference here in the right-hand rule we learned before is that instead of velocity of the moving charges, it's now the current. But the current points in the direction of the velocity of these imaginary positive charges, so it works. In this case, then, an example. So we want to put our fingers into the board. So again, these X's refer to a magnetic field pointing into the board. We want our thumb to point to the right, and we can see that our palm is pointing up. And so in this case, there's a force pulling on this lovely current-carrying wire in the upward direction. That's the application of our right-hand rule. So let's do an example problem here. So the problem we're going to tackle here says a wire with a 10.0 amp current directed west horizontally and a linear mass density of 0.50 grams per centimeter is suspended vertically in the air due to the presence of a magnetic field. What is the magnitude and direction of the magnetic field? So we'll start by drawing a free body diagram for this wire here. It's just kind of hovering in the air. It's suspended in the air, we're told. Well, just as anything else on planet Earth, this thing is going to have a weight associated with it, and that weight is equal to mg. And there must be a force in the opposite direction if it's hovering in midair. So there must be an equal magnitude but opposite force. And in this case, that's the magnetic force, which for a current carrying wire in a magnetic field is ILB, or in this case, I really should write it the way I did right there. So we'll make it BIL sine theta. And again, because it's hovering in midair, it means that the sum of the forces in the y direction add up to 0. That means that BIL sine theta minus mg equals 0, or that BIL sine of theta is equal to mg in this case. All right, now the question is, what is the strength and direction of the magnetic field? So we're going to solve for B here in a little bit, but we also want the direction of the magnetic field, and we have everything we need to figure that out. Now, everything we've kind of done up till now, we're usually given the direction of the velocity or current in this example, and then the magnetic field, and we're asked to find the force coming out the palm. But this one's a little bit different. We're told that this force, in this case, or at least we're able to deduce that the force points upward, so our palm needs to face upward, and then the current is pointing to the right on my diagram, which is to the west. And so in this case, my thumb needs to point to the west, so my palm needs to face up, and the only way that's possible is if my palm facing up, thumb to the right, and my fingers going into the board. But again, we don't have an into the board, out of the board situation. Things have been defined in terms of north, south, east, west, up, and down. And so in this case, my thumb points west, so my palm faces up, and that leaves my fingers to go into the board, which is north. And so in this case, the magnetic field direction is north. All right, so far so good. It's going to mean a couple of things here in our calculation. So one, that means that if the current is facing due west, so and the magnetic field is due north, they're 90 degrees apart, and the sine of 90 is 1. And so that term is going to go away. And so in this case, we rearrange this and solve for the magnetic field. We're going to get the magnetic field equal to mg over IL, and life is good. Now, a couple things. We were given the linear mass density in this problem. And a linear mass density is a mass per unit length. So in this case, it was given as 0.50 grams per centimeter. And if you didn't realize it was mass per unit length, you could see the units, and it's mass per unit length. But before we plug it in here, so notice we have mass per unit length in the problem. So I can rearrange this just a little bit, and we'll say it's B equals mass per unit length times G times I. We can plug these in, but we can take that mass per unit length as just one value. But again, we got to get into SI units to start with. And so in this case, 0.50 grams per centimeter. So 1 kilogram is 10 to the third grams. So we're going to divide by 10 to the third. And then 1 centimeter is 10 to the minus 2 meters. We'll get rid of those. And so in this case, we're going to divide by 10 to the third and divide by 10 to the minus 2. And overall, what's left, we're dividing by 10 to the first, which is going to reduce this down to 0.05 kilograms per meter. Times gravity, 9.8 meters per second squared, all over I, which was given as the 10 amps. And there's m over L times G over I. We'll let our calculator do the rest of the heavy lifting for us. All right, so 0.05 times 9.8 divided by 10. And we're going to get 0.049 here, and that's got 2 sig figs. That's going to be in units, SI units of Tesla. And in this case, that's pointing north. So the last part of the lesson focused on a current carrying wire and the magnetic force it would feel in the presence of an external magnetic field. But in this part of the lesson, we're going to learn that moving charges, and current qualifies, also create another magnetic field as well. That's going to be the focus here. And there's a simple formula for the magnetic field created around a current carrying wire. It's mu naught I over 2 pi r. Mu naught is a constant, permeability of free space. I is the current, and r is how far from the wire you are. kind of like radius, if you will, and we'll see why we might want to call it radius. And so it turns out there's a right-hand rule for figuring out the direction, and it's going to be similar in defining some of the parts of that right-hand rule, but it's going to have a little bit of a twist from what we've seen. So in this case, we're still going to have your fingers going with the magnetic field, and you're going to have the current going with your thumb yet again here. But there is no force in this particular right-hand rule. Notice there's no force in this equation. There's no third part of this right-hand rule. And that's what's going to be a little bit different here, is there's no palm defined here. You're going to put your thumb in the direction of the current, and then your fingers actually curl around the wire showing the direction of the magnetic field. It actually goes around in a circle around the wire. And it's either going to go around one direction or go around the other direction. And you figure that out by figuring out which way the current flows with your thumb, and then your fingers wrap around in that direction. And so in this case, we can kind of see that it's wrapping around this way. And so it's not in any one constant direction. It's going around in a circle. And so depending on if you're in front of the wire, behind the wire, above the wire, below the wire, the direction's going to be a little bit different. So if I said, what is the direction of the magnetic field caused by the current in this wire? Right above the wire. Well, I do my right-hand rule, thumb pointing to the right with the current, and right above, it's curling around, and right at the moment we hit the vertical part, or the top part of the wire here above it, it's pointing straight out of the board. What if I said right below the wire here? Well, curling around, as it goes around, it would be going right into the board right there. What about right in front of the wire? Well, right in front of the wire, as it goes around, it would be pointing straight down. Right behind the wire, it'd be pointing straight up. So, and that's kind of how that works with the magnetic field wrapping around. And then for the magnitude, we have a lovely little plug and chug formula here. And the further you get away, though, the smaller it gets. So if you're twice as far from the wire, so your magnetic field strength is going to be cut in half here. So the first problem we're going to take a look at is a classic problem involving what we call parallel conductors here. So we've got two parallel conducting wires, and the question says, is the force between the following two wires attractive or repulsive? What would be the effect of doubling the current in both wires on the force between the two wires? So a couple tricky parts to this. So one, we have two different right-hand rules showing up in the same problem on two occasions, and that's going to be a little bit of a pain in the butt. And so the direction part of this is going to be a little bit tricky. But even the calculation we'll see is going to get just a little bit tricky as well. All right, so let's start with some directions here. So what's going on here is that both of these are creating a magnetic field, a la this equation, and then each wire is feeling the magnetic field created by the other wire, a la this equation. And that's why we're going to get the chance to apply two different right-hand rules, because we got two of the different equations at play at the same time. Now to make this a little better here, I've been using the convention of using red for current, but I want to draw these two in a slightly different color if possible. So I'm going to make one of these purple. That's going to make this a little easier to see for this problem. All right, so what we want to do is figure out, let's start with either one of them. I'm going to choose the one on the left. I want to know what force does he feel. Well, again, he's feeling a force, again, a la this equation, due to the magnetic field, a la this equation, that's caused by the other wire. And so now we'll start with, okay, well, what's the direction of the magnetic field that this wire is causing where the other wire is located? So we're going to start with this right-hand rule right here. We're going to put our thumb in the direction of the current, and then we're going to curl around the wire. And so what that means is everywhere off to the left of the wire over here, it's coming out of the board. So whereas everywhere off to the right of this wire, if we cared, it's going into the board. Well, I don't really care about that because there's no wire over there. But there is a wire over here. And so the magnetic field that this wire feels is coming out of the board. That's the direction right at its location. Okay, so now we apply this right-hand rule to figure out what force this wire feels. And in this case, we're going to put our fingers again in the direction of the magnetic field that it feels, its thumb in the direction of the current, and out our palm will come the force. And so again, thumb down, fingers coming out of the board, and I can see that there's a magnetic force pointing to the right coming out my palm in this case. So there's a force pulling it away from the other wire, so to speak. Okay, so now we want to do the same thing for the other wire. We'll erase what we've drawn so far to make this a little simpler. So we already talked about the magnetic field created by this wire that the other wire felt. Now we want to talk about the magnetic field created by the red wire that the purple current wire is going to feel instead. And so once again, we apply this right-hand rule down here with our thumb in the direction of the current. The magnetic field created curls around the wire. And what that means is that it curls around the wire, that it's going to point in everywhere left of this wire, but it's going to point out everywhere to the right of this wire. And again, I don't really care what's going on left of this wire because there's no other wire over here, but there is the wire over here, and it's feeling a magnetic field that points out of the page here due to the other wire. And so now we'll go back and apply this first right-hand rule to see what direction the force is in. And so we're going to have our fingers coming out of the board. We're going to have our thumb pointing up. And so right-hand rule shows that it's going to be pointing, what looks like to me is my left, but to you it's going to look like pointing off to the right is where it comes out the palm and is the force. And so taking those two forces that we determine the directions into account, there is a repulsion going on between these two wires. The forces they feel are away from each other. And it turns out we can make a generalization, that it's handy if you remember it. But it turns out if you have two parallel conducting wires, if their currents are in opposite directions, it's a repulsive force. If you put these two currents in the same direction, either in this case like both up or both down, it turns out there would be an attractive force. How you remember that? If you think like in terms of charges, likes repel and opposites attract, but with current carrying parallel conductors, likes attract and opposites repel. I don't know. So it's helpful if you do remember it because we went through a lot of work to figure it out, and you'd be a step ahead if you did. So the second half of the equation is dealing with the calculation though, and it talks about if we doubled the current in both wires, what would be the effect of doubling the current in both wires on the force between the two wires? And it's a little bit tricky because if we look at the equation again, here we get force equals BIL sine theta. And I said, well, I'm going to double the current in both wires. Well, that's where it shows up in the force equation. You double the current, you double the force. They're directly proportional, done, doubled. Except we missed one thing. And the one thing we missed is that where does this magnetic field come from? Well, the magnetic field that's a part of this equation for the force of the other wire is from this equation. And so maybe I call this the force felt by wire number 1 is related to the current in wire number 1, but it's related to the magnetic field created by wire number 2, which involves this equation. So I'm going to substitute that in, and so I'm going to have the force felt by wire number 1 is equal to mu naught I over 2 pi r, substitute it in, where it's the magnetic field created by wire number 2, which involves the current in wire number 2, and then again times I1L sine theta. And all of a sudden, now we see that both I1 and I2 actually indirectly show up in the force felt by either of them. And in this case, they feel the same magnitude force. It's an equal magnitude force in opposite directions according to Newton's third law. And so if you double both currents, the force is actually going to quadruple in this case. So, and had we not done the substitution here, we might have totally missed it. And so doubly tricky. Two sets of right-hand rules applied twice, and then a substitution here to make sure that you realize that doubling both currents quadruples the force felt by each of the wires. So now we want to take a look at the torque on a current-carrying loop in an external magnetic field as depicted here. Now, quick reminder that torque is equal to force times lever arm, and if you use L for lever arm, props to you, I'm going to use delta R to be consistent with what I used earlier in the course. But that's going to be our running definition of torque. Now, it turns out in this context, the nature of that force is the fact that we have current running through wires here in a magnetic field. So it was the F equals BIL sine theta. That's the force that's at play here. Now, there's an overall equation for the torque here that's equal to the strength of the magnetic field times the magnitude of the current times the area of the loop. Now, I'm going to make it a rectangular loop to make this a little bit easy, but it could be any shaped loop. And as long as you can calculate the area of it, you plug it right into the equation, and then the number of turns, which in this example would be 1, but again, you might have a loop that's 100 turns over and over and over again, and you plug in 100 there. And then sine theta, and we got to learn that theta here is going to be defined a little bit special, and we'll come back to that in a little bit. Okay, so let's talk a little further about the nature of the force being felt here. So I'm going to start with the current going through this upward part of the loop here, and we learned a right-hand rule for figuring out what the direction of the force on that current carrying wire is going to be. And because the current is in different directions in all the different parts of the loops here, we're going to have to actually find the force, or the direction of the force anyways, with a different application of the right-hand rule every time. And so here we'll put our thumb in the direction of the current, we'll put our fingers in the direction of the field, and the force comes out the palm. And so on this loop right here, there's a force going into the board. If we go to the opposite side here, we get the opposite result, because now the current points down, and so my fingers still need to point to the right with the direction of the magnetic field, my thumb points down, and now coming out my palm is out of the board, and we can see the nature of the torque here. We're pushing this loop in on the left-hand side and pulling it out on the right-hand side, and that's why it wants to rotate. We're going to find out that this horizontal portion right here, that is parallel in this case to the magnetic field and anti-parallel in this case, makes no contribution because there's no force. Keep in mind that again, if theta is either 0 or 180, if the current and the magnetic field are either parallel, like they are in this part, or anti-parallel, like they are in this part, the force is 0. So no contribution to the torque here or here whatsoever. Now we want to define a couple of things here. And so let's say we make this dimension right here our width, and we'll make this dimension right here our length. And then we want to kind of do some plugging and chugging for our torque here. And so in this case, if we look at the contributions to the torque, we got the force, which in this case is going to again be BIL sine theta. So I'm going to leave sine theta out for a second. So in this case, for this part right here, the magnetic field and the current are 90 degrees apart, and sine of 90 is 1, and so it just kind of falls out in this particular example. All right, so BIL, and then our lever arm distance. So it turns out this is going to have an axis of rotation right down the middle here as it rotates. And so that axis of rotation here is going to be W over 2, 1/2 W. And so the force is BIL, and then times W over 2. And that's going to be the contribution from this part right here, but it's also going to be the contribution from this part over here as well. And so that's going to be BIL times W over 2 as well, or 1/2 W. Cool, and there's the two contributions to our torque. And if we add those together, we're going to get BIL times W. Well, what's length times width for a rectangle? Well, length times width is the area. So this is going to reduce down to B times I times the area. And we can kind of see how this is lining up with our equation right here. So B times I times the area. And then N here would be if we had more than one turn. Well, with just one turn, it was just times 1. But if you had 2 turns, then you'd have these terms doubled. You'd have 2 of these terms and 2 of these terms. If you had 10 turns, you have 10 of these terms and 10 of these terms, and effectively you're just multiplying the entire equation at the end by 10 with 10 turns, or by 2 with 2 turns, so on and so forth, and that's why that shows up in such fashion. Okay, so now we got to talk about that pesky sine theta here. So it turns out if the loop is parallel with the magnetic field, you get the maximum in this case. So how is theta being defined here? Well, it turns out that theta is being defined in such a way that it's not the angle away from the magnetic field. Because if it was the angle of the loop away from the magnetic field, well, I'm saying it's at a maximum when there's no angle between them, when it's 0. But the sine of 0 would be 0, so that doesn't work. And so the way they've defined this is that theta is actually not the angle between the plane of the loop and the magnetic field, but between the plane of the loop and the normal to the magnetic field. Well, the magnetic field's in the plane of the board. The normal is right here. And right now, the loop is also in the plane of the board. It's perfectly perpendicular to the normal. So how far away are we from the normal? If we're perfectly perpendicular to it, we're 90 degrees away, and the sine of 90 is 1. So it's really tricky here. Students get hosed up on this one quite a bit, but the key is that theta here is defined differently now. It's not the angle of the loop away from the magnetic field, but away from the normal of the magnetic field. How far are you from being 90 degrees away from the magnetic field effectively? Well, here we're 90 degrees away from being 90 degrees away from the magnetic field. Cool, so that's where this lovely equation comes from. Let's do an example calculation. So the question says there are 100 turns of wire in the shape of a square loop with sides of length 10.0 centimeters and having a current of 12 amps. Calculate the maximum torque on this square loop in a magnetic field of 0.50 Tesla. It's going to be total plugging and chugging here. So again, torque equals BIAN sine theta. Now, if we're going to calculate the maximum torque, that means our loop must be parallel to the magnetic field. That way, we're 90 degrees away from the normal, and sine of 90 is 1 to get the maximum. Okay, so we'll go there, and now it's plugging and chugging from here. So torque equals magnetic field, and that's given as 0.50 Tesla, times the current, and in this case given as 12 amps, times the area. In this case, we're told it's a square, and it's a square with sides of length 10 centimeters. Well, in SI units, 10 centimeters is 0.1 meters. And area of a square is 0.1 meters squared. It's side length squared. And then finally, times the number of turns we're told is 100. And there's our calculation here. And you can probably do this in your head. You could definitely let your calculator do the heavy lifting for you, but I made the math easy. So it turns out that 0.1 squared, this is 1/10 squared is 1/100th, and 1/100th times 100 is 1. These two terms cancel each other out. And you're really just left up with 1/2 times 12, which comes out to 6. And my question for you is 6 what? So, well, you could go through here and be like, well, it's a Tesla amp meter squared. And that's true, but you might be better off just looking back and reminding yourself what the units for torque are. And it's force times lever arm, which was force newtons times a distance meters, and it's a Newton meter. And to get 2 sig figs, I should have made this 6.0 Newton meters. If you found this lesson helpful, consider giving it a like. Happy studying.